This is Paul Cronius. I'm back here again on day 3 of solving Algorithms 1 from Leetcode. Here to learn, like we just said. So as we said the previous times, we're going to continue to work through problems, talk through them out loud, and if anyone in the chat comes through, kind of answer questions and kind of rubber duck some of these things. So I wanted to talk about some of the things I'll be doing the next several weeks and hopefully months. It'll be a lot of algorithms because I'm fundamentally interested in improving my ability to do logic as a developer. But there are a few areas that I'm interested in actually outside of this. Primarily, I actually am interested in making my first game. So I believe the tool set that I want to use to make my first game will be Unity. So I believe over the next couple of weeks, I will start to do a couple of Unity-based streams, and probably a lot of it will be me just going through the tutorials initially, kind of making a simple MVP, minimum viable product, just kind of using the stuff that they've already given me. And then eventually my plan is to kind of figure out what would be a small game that I could write and put together, kind of talk through my logics from stream to stream with something eventually that I would publish to itch.io. So that's kind of the long-term goal here. It's going to be a lot of coding, a lot of algorithms, a lot of game development, and even maybe later this year we might get into a little bit of data science. But that's the future. Today we're going to do a little bit more Leetcode and a little bit more algorithmic analysis. So today let's start with Leetcode 35, search insert position. So as always, let's go ahead and start with the problem statement. Given a sorted array of distinct integers and a target value, return the index if the target is found. If not, return the index where it would have been if it were inserted in order. Or in other words, basically, if it should have been there, but it's not, tell us what index it should have been if it theoretically was in the list. Okay, so, and the note that they give is you must write this algorithm with O log n runtime complexity. So what does that mean? Well, as we've discussed the past couple of streams, what that means is that we want to have the space of the problem every time we do an iteration. So because it's in sorted order, we can basically have the space each time we do an iteration, and essentially we should be able to solve the problem worst case in roughly half the size of the list iterations. Now, if this list was not sorted, and certainly problems in the future will be unsorted data sets or even sets with dupes as a potential possibility as well, the best case for kind of figuring out what's going on might actually end up being n log of n. And the reason why is if you can't guarantee, if the list is not sorted, at minimum, you're probably going to have to look at every single item in the list to figure out if you're finding something, which makes sense, right? Like you don't, in the worst case, you might not have the value you're looking for, or conversely, if you guarantee the values in the list, at worst, it actually might be at the very end. But if the list is not sorted, then we have to do something clever like sort the list, which we'll learn later. The best time complexity sort really we have at our fingertips that's relatively easy to implement is n log n. So, you know, it's not going to be quite log n. We're getting away with a lot of these problems doing log of n analysis because, again, the problem is stating that all of the lists are actually sorted. So that's why we're getting away with it. So let's look back at the problem. So now that we've kind of described the problem and what we're trying to do right now, let's look at some of the example cases and kind of understand what they're expecting from us in this case. So example 1, given a list of nums 1, 3, 5, 6, and the target 5, it expects output 2. So again, as we discussed last time, in JavaScript, lists are 0 indexed. So what this means is that the number 5, it's in 1, 2, 3. It would be position 3 if we were 1 base index, but since it's 0 indexed, we're going to actually be at position 2. So 5 is at 2, and that's the answer. Example 2, given 1, 3, 5, 6 with a target of 2, we expect the number 1. Now this is going to be confusing a little bit compared to some of the other problems that we've done the last 2 days. But if you look at this list, 1, 3, 5, 6, and you're looking for the number 2, where would we expect it? Well, since this is a sorted list in ascending order, we would expect the number 2 to be between 1 and 3, right? Because 2 is between 1 and 3. In that case, that would now become index 1, which is why the output now is 1. So I think now you better understand what they mean by if it doesn't exist in the list, tell us where it should have been. And that's something we should be able to accomplish with, drumroll please, binary search, which is what we've been basically doing the past 2 days. All right, finally, the last example. Now, this is a good corner case to think about. Given a list of 1, 3, 5, 6 and a target 7, what is the index where 7 should be? Well, the greatest value in the list is 6. So what that means is that 7 should be a new entry in the list, which would be at index 4, since the list would now be 5 entries. So overall, not super complicated of a question. We just have to be careful because it's entirely possible the number that's missing could be at the beginning or the end of the list. Or in the best case scenario, it's actually a member of the list, in which case it's a simple binary search result, or we have to figure out where in the list it should have been as a number. Okay, so without that being said, I believe we should take this with an iterative approach, and we're going to do something very similar to what we've done the past 2 problems, which is basically define 2 pointers, which are at the start and the end of the list. And what we're going to do is we're going to keep iterating until the beginning pointer in the list, or in other words, kind of like the placeholder in the list, crosses the end one. And when they cross, or we basically find the target, then we know either we found the target words in the list or we return the index, or when we cross, we know that whatever index that is, that's where it should have been if it existed. So I think that is the kind of like out loud whiteboard analysis of this. So let's just kind of frame this out in the function and then see if we can start to fill in the pieces. So again, like I stated, let's start out with, and I'm sorry, I apologize. The last thing we should look at, and again, always look at this before you start the problem, are what are our constraints? So our constraints is that the list of numbers is between 1 number and 10 to the 4. So we're not dealing with overflows here. And the list is guaranteed at least to have 1 result. So that's good. The numbers can be negative or positive between that range, which is fine. There's no issue using binary sort if the numbers are negative or positive. Nums contain distinct values sorted in ascending. Okay, this is very important, and it kind of goes back to what we were talking about. These style of binary search algorithms really work if all the numbers are distinct and they're sorted. Otherwise, to use binary search on an unsorted array of numbers, you actually would need to sort the numbers first. If there are non-distinct numbers, which basically means you have repeated numbers, then we have to kind of think about how to handle that. I honestly have never tried to modify binary search to work with a list of non-distinct numbers. I feel like that's something we probably will tackle one day, in which case we might want to do something different. But, as we discussed, I think we cross that bridge when we get there. Today, for the sake of this problem, we're just dealing with distinct ascending numbers. So we know that binary search with 2 pointers is probably the best approach in this case. All right, and finally, the target number also is within the range of negative 10 to the 4, 10 to 4. So again, easy numbers for us to deal with from a low-level language perspective. All right, so let's get started here. Oh, and by the way, I'm continuing to tinker with my setup. Again, I'm new to streaming, so I apologize if it doesn't sound necessarily the best. I probably will be investing in an arm for my mic in the next couple of weeks. And eventually I'll be looking to set up a mirrorless camera I have as a webcam. So I think if you're patient as I continue to kind of learn how to be a better streamer. All right, so let's get started. So like we said, we need a start and an end pointer to perform this. So we're going to define the start as the beginning of the list, which is 0, because it's a 0 index list. And then we're going to define the end of the list, the end pointer, as the end of the list, or the index of the end of the list. In this case, it's going to be the length of the list minus 1. Now remember, it's the length minus 1 because length will return you how many items are in the array, but the index is going to be 1 less than that. Because again, like we discussed, we start at 0. So if there are 5 items in the array, the max index, or the max part in the list, is going to be 4. So 5 minus 1 is 4. So that's why we're doing this. All right, so that's the initialization. Now, one thing we're going to do, which I like to do personally for these kind of problems, especially when it's basically of 1. You know what? Actually, we'll talk about optimization later. What I was really going to try to get to was the fact that if there's only 1 number in the list, then we can simply first check to see if it's the target. If it's the target, you return index 0, right? Because it's a list of 1 length. But if it's not the target, then you have to basically return either 0 or 1, depending on if it's greater than or less than the target. Actually, you could... Okay, you know what? I said it, so let's go ahead and code the condition. I'll show you the quick shortcut. It's not going to be the prettiest of code, but this theoretically should work. So if nums.length, if the length of the list is 1, what we can then do is return a ternary. So in this case, a ternary says evaluate a statement. If it's the first, if the condition is true, do the first condition, otherwise do the other condition. Now you can nest ternaries, which I'm a huge fan of not doing, because nested ternaries can get, there are places for it, but I tend to avoid trying to do nested ternaries. But for today, we just need a single depth ternary, so that's what we're going to go ahead and do. So in this case, what we want to check is the nums at 0, so basically is the only number in the list, apologies, equal to the target, or the 2 bars mean or in JavaScript and pretty much most programming languages that I'm aware of. I think, although I think Python actually uses the word and or, which we'll be getting to Python later this year. Or nums at 0 is basically less than the target. So if nums at 0 is the target or it's less than the target, the index it should be at is 0. So it's either at the value of 0 or it would have been before it, in which case then the list grows to 2. If it doesn't meet either of these conditions, that means that the number is greater than the target. If it's greater than the target, then it should be 1, because it would be the second number in the list. So this code right here basically is a micro optimization, especially if, like, as a developer, you knew your data set had a lot of lists of size 1. This would be a great thing to do because this computation is O of 1, right? Because irregardless of the size of your list is going to be 1. So you're going to short circuit doing a loop and this additional logic, and you're just evaluating a simple logical statement. So this could speed up your code. Now, if you know most of your list values are not going to be 1, amortized over all of the data you're looking over, this might be a useless optimization, but we'll just keep this here for now, just kind of as a example of code we can use. All right. Now that that's done, so we set start to 0 and end to the last number in the list. Let's go ahead and define our loop, because it's an iterative solution, which means we're going to iterate through the list until we basically no longer are in the condition that we iterate in. So in this case, just like yesterday, while start is less than or equal to end. And the idea again being, if the left pointer or the left thing pointing to the list crosses over the right, we know that we've finished iterating through the list and we're done. So that is our condition that will basically end the looping. So what are we going to check? Well, the optimistic case 1, is going to be that we found that, oh, sorry, before we get to case 1, we need to define the middle, right? Binary search is about finding the middle value between 2 endpoints and then seeing if that's the value, right? So again, we'll just do a very simple middle. We won't do the overflow version because we're not worried about overflows in this case. So in this case, middle is going to be start plus end divided by 2. And again, because indices are whole numbers, we're going to take the floor to make sure that we're always indexing with a whole number. So an example of this would be, if your endpoints are indices 1 and 2, 1 plus 2 is 3 divided by 2 is not a whole number, right? So just to break the tie and make sure it's a whole number, we will just always floor the result to ensure that we are at a whole number. Okay, so that's middle. Now, let's go through the cases. So case 1, middle is the target. So in this case, we make a guess, and the guess is actually equal to the target. So if nums at middle is equal to our target, then we're going to return middle, and we're done, right? Because we found the index that applied to it. Awesome, and we're done with our iteration. All right, case 2 is going to be if nums at the middle pointer is less than the target. All right, so let's code that. Let's code this else if condition. So else if nums at middle is less than the target, then what this means is that our guess was too low. So that means we need a higher value. So in order to make the value higher, we are going to move the start pointer to the current value plus 1. Because we know that that value is not it, so then we need to move up 1 index because we already knew that the start pointer was not the value. And this was the trick we kind of got stuck on yesterday, realizing that in order to not fall into an infinite loop, we need to make sure that we bypass it by 1 because we've already eliminated it. So in this case, start is going to equal middle plus 1. Now the last condition we could possibly fall into this binary loop is case 3, and basically middle is greater than target. Now, we don't actually need to define that explicitly because this is the only logical place we have left, so it's kind of implicitly the catch-all condition or the else. So if this is the case, and we need to basically shrink the list the other way. So we need a smaller number, so we're going to move the end pointer into the middle. But similar to like we just did on line 21, we're going to make it middle minus 1. So we're going to go 1 in more than the middle because we already know that middle is not the right value. All right, so looking at this code, have we finished? No. So if this was yesterday, where the target is even yesterday, there's no guarantee that when we're looping through this loop, we're going to find a number, right? And that's because in the explanation, if not, return the index where it would be if it were inserted in order. So in other words, what it's telling us is you could get a list in target where the target doesn't exist in the list. If that happens, we're going to fall out of the loop because essentially what's going to happen is start is going to cross over end and we're going to be done, right? So as a fallback to handle that case, I believe, and we'll mental model test this in a bit without running the code, what we should do here is we should return, and so this is where I really need to think a second because I'm not entirely super confident which is supposed to be here. I believe we want to return start because start is the value that crosses over, and that crossover value is likely where the value should be, but we'll find out if I'm correct in a second. Okay, so now that we've kind of written our algorithm and we've talked through it, what we believe to be a valid algorithm, what we should do is take our test cases and manually run through them and see whether we get the expected result. So let's take a look here. So example 1, nums 1, 3, 5, 6, target 5. So let's go ahead and comment out my cute little micro optimization. It's not really necessary. This should be able to solve itself. So we can kind of focus more on what's going on in the main loop. All right, so we start is set to 0, end is going to be set to 4. So whilst 0 is less than or equal to 4, that's true. Middle is going to be 0 plus floor 4, which is 2, or sorry, 4 divided by 2 is 2. And the floor of 2 is 2. So first condition, is nums at 2 5? In this case, yeah, it actually is. So if 5 is equal to 5, and we return the middle, and we should get the answer. So good. Example 1 seems to work as expected. Let's go to case 2. Nums 1, 3, 5, 6, target 2. So same thing like we did before. Middle is going to be 2 again, because 4 plus 2 divided by 2, floored, is 2. So nums at 2, is it equal to the target? The answer is no, because nums at 2 is 5, and the target is 2. So in this case, 5, which is the value we guessed, is higher than the target. So it's gonna skip case 2, and we're gonna fall to case 3. Middle is greater than target. So middle is 2, so the end becomes 1. So let's do our little visualizer like we did yesterday. So initially we started at 1, 3, 5, 6. And after this, after we finish this iteration, the end is now 1. So the list has basically cut down to 1, 3. All right, let's run the iteration again. So while start is less than or equal to end, so start is 0, end is 1. So this condition, 0 is less than or equal to 1, condition holds. So, and I'm wondering now if actually this needs to just be less than, but let's keep walking through the solution and see if we've accidentally created an infinite loop again. All right. So middle is going to be 0 plus 1. 1 divided by 2 is less than 1. So that's going to be 0, right? So in this case, the middle is going to be 0. So is nums at 0 the target? So in this case, is 1, because nums at 0 is 1, is 1, 2? The answer is no, it's not, right? And in this case, it's less than the target. So we're going to hit case 2. So in case 2, what happens is that start is middle plus 1. Well, we know middle was 0. 0 plus 1 is 1. So the start now becomes 1. So here's what we're left with. So I think actually what happens here, so this is where we need to think now whether we're on the right track. So we have the case where, okay, I think this still works. Let's walk through it, but I think this still works. So now we're at 3. So start and end are the same. So 0 is less than or equal to 0. That's true because it's a size 1 list and there's one entry at 0. Is nums at 0 the target? So nums at 0 is, and I think I did this wrong, by the way. I think, yeah, it's not, right? So nums at 0 is still going to be 1, correct? So that's not the right value. So what in this case, you know what? Let me make sure I've done this correctly. Let me go back and just iterate through it again real quick. So we're here, and then we guessed 0, which is 1. 1 is less than the target. So the start basically became 1. So they're both pointing through. So yeah, that was correct. So they're both at 1 at this case. This is where it gets tricky to do this representation because it can be a little confusing. So we have to really, it probably would be better when I do this, to be honest, is just to draw a little pointer above it like this. So this is start and then this is end. So start and end. Let's do it this way moving forward because it's a little bit clearer what's going on. Okay, so 1 is less than or equal to 1. True. Middle is going to be 1 plus 1 is 2 divided by 2, which is 1. So in this case, is middle the target? The answer is no. And in this case, 3 is greater than 2, right? Because the value here, 3, is greater than 2. So we go down here. Middle is greater than target. So in this case, the end now becomes the middle, which is 1. It becomes 0. All right. So now we see we're about to cross our case, right? So in this case, now when we come back up to the loop, is start less than or equal to end? And the answer is no, because start is 1 and end is 0. So this loop terminates because we've now basically finished out. So now we come to here. So if we look at the code we've written, start is at 1. So it's saying the value 2, if it existed, should be at 1. And guess what? That's exactly what the answer is. Output's 1. So this case would appear to be correct. All right, let's test the last case when it's at the end. All right, so I'm going to reset our start and end pointers here. I'm going to re-expand the loop so we can kind of see what's going on here. So start and end. All right, so here we go again. So just like the other iterations, the middle is going to be 2 because it's 0 plus 4 divided by 2 floor is 2. So is nums at middle 2, so is 5 equal to 7? And it's not. And in this case, it's less than the target because 5 is less than 7. So what do? We hit case 2. So if it's less than the target, the start becomes the middle plus 1. So in this case, middle was 2. So start and end are back to being in the same index, and we do the loop over again. So while start is less than end, 4 is less than or equal to 4. That's true. All right, so the middle in this case is going to be 4 plus 4, 8 divided by 2, 4 floored is 4. So we're still on index 4. So is 6 equal to 7? No, it is not. And what are we? We are still less than 7. So we fall to case 2 again. So what happens in this case? Well, start is going to be middle plus 1. What was middle this time? It was 4. So, and we'll have to do a little imaginary here, but this S is sitting over here in imaginary where it should have been 0, 1, 2, 3. Yeah, so it'll be an imaginary index 4 because this is list of size 4, this is index 3, and this would be 4. Okay, cool. So run the loop again. Well, start is not less than end. Start is greater than end. So we fall out of the loop again, and so we return start. And the index of start is 0, 1, 2, 3, 4, 4, and that's the answer. So as far as I can tell, this algorithm meets all the test cases that were provided. So let's go ahead and delete this code. That's going to cause us to have a type error, right? Because it's not real JavaScript. And let's run the base case, which I believe will be example 1, and see if we get a passing value. And we do. All right. Do y'all feel confident we got the right answer on our first try? That would be first, because yesterday was a real struggle, to be honest. All right, but I'm feeling good. We went through our examples. I think I went through them well. It seems to be working okay. If we want it to be complete, we could do one more example. Do you guys want to do one more corner? Yes, let's do one more corner. So the corner I want to do real quick to finally check, to have pretty good confidence that what we're doing is correct, is I want to check the case where the target is -1, which means it's essentially it's not on the list, but it's also to the left, not the right. So let's do the problem with a target of -1 to kind of check ourselves. So it's still size list 4, so we know our middle's 2, and obviously 5, in this case index 2, is not equal to our target at -1, and the target in this case is, or sorry, the value at nums is much greater than the target. So we fall to case 3. So in this case, end is going to be middle -1. So middle was index 2, so end is now index 1. Run the loop again. Start is still less than or equal. That's great. In this case, the middle is going to be 0 plus 1, which is 1 divided by 2. Floored is 0. So our middle is 0. Now, is nums at 0 equal to the target? No, 1 is not equal to -1. 1 is greater than the target. So we go to case 3 again. So end, so we just said our middle was 0. So now end falls way, way down here to -1 index, which makes no sense in this context, but it still works for the sake of the problem. So start is greater than end now, right? So the loop is terminated, and we return start. Well, what is start in this case? 0. And that's exactly what we expect, right? Because if we were inserting -1 into this list, it would be at index 0, because it's in ascending order. So I have good confidence that we have solved this algorithm. So we've done our corners, we did our kind of what we did. We did what we would call our whiteboarding if I was physically drawing on the board, which, to be honest, might happen eventually. But I think this presentation is fine for these initial problems. All right, we're going to hit submit. Fingers crossed, y'all. And we passed it on our first try. Give a hand, everyone. That was a great solve. I hope you learned something from doing that one. That felt great. But I think doing it the last 2 nights, really, and struggling a little, to be honest, kind of solidified what the approach was here. Okay, so since we finished that in about 27 minutes, I'm going to refresh this to get credit for solving this problem. And we'll go back into algorithms. Oops, I apologize. So we finished all the binary search problems. I think at this point, no pun intended coming up now, I think we're ready for 2-pointers. So here's the thing. I'm actually pretty behind on this. I'm supposed to be on day 4 already, because we're supposed to be doing 2 problems a day. But to be honest, I don't know if I even know how to do some of these problems yet. So trying to do 2 of them in like a 1-hour session is probably asking for a lot. But, let's do 1 more today, and maybe tomorrow we can try to do 2 more. So maybe we can try to do 2 a day or so and see if we can catch up. Otherwise, it's no big deal. We just copy the problem numbers down, and then we continue to work it even if I run out of the training plan. But fingers crossed, as we continue to do problems like this over the long term, we solve them quicker, right? All right, so let's go into problem 977, squares of a sorted array, which has a pretty high acceptance rate. So maybe we have a shot at getting this done in less than 30 minutes. All right, so I'm going to click start now. Let this load in real quick, and I'll take a sip of coffee. Coffee is my lifeblood, y'all. I'm a huge coffee person, so yeah, anytime I'm really trying to focus in, coffee definitely is like an absolute huge thing for me. So it's always by my side at my desk for sure. All right, let's get to the problem. 977, squares of a sorted array. Given an integer array nums of sorted in non-decreasing order, which is just a way of saying it's getting bigger and bigger, return an array of the squares of each number sorted in non-decreasing order. So basically in increasing order as well. So this is a very, very interesting problem. It seems really trivial at first, right? But what you'll see as we start to go through the examples is it's not so trivial. And the reason why it's not trivial and why this is called a two-pointer, or this is a two-pointer problem, is that you have negative numbers. And those negative numbers, when squared, right, a negative times a negative is a positive, those could be larger than a corresponding positive number you're comparing to. Thus, why we're going to use two pointers to solve this problem. Let's go through the examples first, so we have an understanding of what the ask is, and then we'll start to kind of pseudocode out what the solution is going to be. All right, example 1. So given inputs of -4, -1, 0, 3, and 10, we expect an output of 0, 1, 9, 16, and 100. All right, how do we get to this list? Let's talk through that real quick to make sure we understand how we're getting here. So if we look at these numbers, the smallest value you could possibly get from this list of 5 numbers is 0 squared is 0. So it logically goes there. The next lowest one would be -1, because -1 times -1, or -1 squared is 1. The next highest value would be 3 squared, which is 9, then followed by -4 squared, which is 16, then followed by 10 squared, which is 100. So y'all see the trick already, right? It's very possible, even though you have negative numbers, a lot of these negative numbers are probably going to be bigger than their companion positive numbers on the right side of the list. So you can't just go through this linearly. In other words, starting at index 0 and moving up to the end of the list, you're going to be in the completely wrong order. So you're going to have to do something ugly. Well, not ugly. It's valid code. But one naive approach to this problem would simply be to square every number and then sort it. So what is the time complexity of sorting the list, basically squaring everything in the list and sorting it? Well, it's going to be n, because you have to go through it once. And then like I just stated earlier in this stream, it's going to be n log n to sort it. So you're looking at 2n log n, but like if you're not familiar with big O, it's okay. I'll kind of give an explanation. We don't care about the 2, and the reason why is the constant value of 2n is much smaller than n going off to infinity, right? Like, so is 2 times infinity is 2 times infinity like comparable to infinity? No, it's infinity. It's literally infinite. So just because you multiply 2 against it, it doesn't really make that big of a difference. Now, that being said, be careful. That is purely from an academic perspective and a starting point when evaluating different algorithms to solve a problem. I think as a junior or even as a senior or wherever you are in your code journey, it's good to know that your data sets are not going to all be infinite lengths, right? You're probably going to have some kind of fixed size to your data. Like it might be, you might deal with a lot of stuff that's 100 items long, or you might even be dealing data that's only 5 to 6 items long, right? In that case, 2n log n actually starts to, have more appreciable value, right? Because as n gets less and less, as it starts to move away from infinity and become more of a finite number that we're used to managing, then those constants are a much bigger deal, right? Because 2 times 10 halved is like, let's say it's probably something on the order of like 13 or 14. Like it's 14, right? But like in infinity, 2 times infinity is a larger number. So you might want to pick another algorithm if your n is actually a relatively low number. But we don't need to get into that today. And in fact, for my own sake, we probably should do a bigger stream talking kind of about O of n eventually. But for today, let's just focus on the algorithm, in which case we're going to still use a 2-pointer approach for this problem, which will be log of n. And the reason why is we're going to approach it very similar to binary search. I'm sorry, it's going to be n in this case because we have to touch every number. We're not searching for a number. We're basically putting the list in place. So it's going to be n because you have to touch every single number when you go through the problem. So instead of doing n log n, we're going to solve this with n. And the reason why we're able to do this is because the list is already sorted. Again, that's the key. If your list is sorted, then you probably can come with a log n or n solution. Okay, cool. So that's example 1. Let's look at example 2. So it's just another array of numbers, -7, -3, 2, 3, and 11. So if we go through it again, 2 squared is 4, 3 squared is 9, 3 squared is 9, 7 negative squared is 49, 11 squared is 121. Now, what's different about this list versus the previous list in the other example? Well, the example in this case is that -3 and 3 squared both return 9. So if you're not careful with your algorithm, you might get out of sync because you might say, wait, if they both have the same value, which one do I do? Do I do the -3 or do I do the 3? Well, in this case, it doesn't really matter, right? As long as both numbers are selected and eliminated and placed into the new sorted squared list, the answer is good. So what this really means is that it doesn't matter which way we go, whether we pick the left or the right value, the start or the end pointer value when there's a tie, as long as we pick one and move on, the other one will be picked up in the next iteration. So we'll still get the same answer. But this is just trying to show there are non-distinct values in this problem, unlike the previous problems we solved where all of the values were considered. Well, sorry, let me back up a second. There's still distinct numbers, but when we square them, which is the requirement of the problem, we could potentially get non-distinct squared numbers. And that is different than the previous problems we've solved. Okay, now that we've gone through all the hullabaloo, I think I just said that word strangely, but that's okay. Let's talk through our constraints, which is always the next step. So constraints here is the length of the list is between 1 and 10 to the 4, so not going to overflow, and we know at least one value will be in the list. And the numbers themselves are between -10 to the power 4 and +10 to the 4. So again, no overflows, we should be good to go. And it repeats what it repeated in the problem statement, that nums is sorted in non-decreasing order. So let's work through the setup, assuming we're going to do a two-pointer approach, which we've just done, for the previous 3 problems. All right, so to get started, we're going to have to define those pointers, right? So let's start is equal to 0. So again, we start at the beginning of the list, and let end is going to be the last index in the list. So in this case, like the previous problems, it's going to be the length of the list minus 1 because lists in JavaScript are 0 indexed. Okay, so now that we have these two, this is the part that's going to be slightly different than the previous problems. So we're not finding a target anymore, right? We're not finding a targeted value. This is not binary search. But what we're doing is we're comparing values using these two, what we call pointers. And then what we're going to determine is which one should be pushed. I'm going to go ahead and push these to a fresh array in this case. It doesn't say it has to be, in some problems that you're going to see, like in algorithms or even in interviews, they might say, oh, update it in place. And what that means is that they want you to take the existing list and update it without creating a new array or basically allocating additional memory. So the way you can get around that is usually you'll just invoke some sort of temporary variable, like so const temp or something like that, and you'll temporarily put values in that so you're able to place things, and you might move it back to the other place. And the reason why that's still considered in place is that the memory allocation for a single temp variable is going to be always constant, right? It's like one space of memory. It depends on your language. It might be several bits, or kind of depends on what the implementation details are of your language at the middle. But from a O of n perspective, that one constant memory allocation for the temp is not going to scale with n, right? So as your list gets bigger, so as n goes to infinity, or your list of things you're squaring goes bigger, you're still always going to have only one single temporary variable. So that's why it doesn't make any impact from a memory perspective, scaling up with the size of the list. I hope that makes sense. If not, I can try to clarify that in a future video. Okay, so that all being said, what do we need to do next? Well, this is going to be very similar to binary search. What we want to do in this case is we want to loop while the start pointer is less than or equal to the end pointer. So the reason that, and I believe this is correct, and of course we'll test this in a second and determine whether this is right or wrong, is that if you have an odd list, you need to check that middle one. So if you have 5 entries, you're going to eventually get to the third one. So start and stop might point to the center value, which is the last value, in which case you want to square and return that. So let's leave that for now. But if I'm wrong, and because I promise I always struggle on this a little bit, but I'm continuing to try to work on this. We might have to make it just a less than. But let's figure that out by doing the test examples and writing the code and kind of see where we end up. Okay. So the first thing we're going to do is we need to square the values at each index to figure out which one is bigger or smaller, or maybe equal in this case, right? So let's do if let's be a little bit. We're gonna write out a little bit more code here. And the reason why is just to make it clear. You probably could kind of shortcut it a little bit, but let's be a little explicit what we're doing. So const start, we'll just say start squared in this case, is going to be math.pow. And we're going to do, in this case, nums at start. And we're going to square it. So we're going to do it to the power of 2. And then const end squared is going to equal to math.pow nums at end 2. All right. So basically what we've done here is we've squared both numbers. And now we're ready to kind of do our comparisons. So let's talk through our cases like we always do, right? So case 1 in this case, no, probably that's a terrible sentence, never use that. Start is less than or equal to end. So remember we talked earlier about what happens when they're ties. So in my case, if the value at the start pointer squared is less than or it just equals the end, I'm going to go ahead and take that value. And so what will happen is the next iteration, whatever's at end will be taken because the value at start, once I increment by 1, which we'll see in a second, once I increment by 1, it will be larger than that value, so n will be taken in the next cycle. But let's code it out to make sure that we kind of understand what's going on here. So if start squared is less than or equal to n squared, and let's go ahead and define a new array here, and this is going to be what we push to. We're just going to push to a new array to keep this one simple. N squared, then what we're going to do is new array dot push. So push is the method to push to a list in JavaScript. We are going to push start squared. Okay, so we push the value that's basically the less of the two, in this case start less than or equal to the array. But now what do we need to do? Well, we need to increment the start pointer, or we need to move it up by 1 because we've already consumed that number in the list. So we're going to do start plus plus, which is the short way of saying take the value start and add 1 to it. Else, case 2, so let's write a pseudocode comment here so it's more clear what's going on. Otherwise, case 2, start is greater than n, so basically the start pointer value squared is greater than the n1. Then we're going to do more or less the exact opposite of what we just did. So I'm going to be lazy, and I'm just going to paste this in and then reformat it real quick. But essentially, and I don't think this web browser, yeah, it is a support command D. That's annoying. So we're going to push the n value squared instead, and then instead of incrementing start, we're going to decrement n. So we're going to go backwards by 1, and then we're going to continue the loop. So we're going to continue going through this list until basically start crosses end. In which case we know we've finished, which would kill the loop. So then what's left? Well, we have an array of values, but the function is not returning anything, right? Right now it's returning void because there's no result. So when we're done with the loop, we're simply going to return the new array. And that should give us back the new value. So this is the algorithm. Again, pretty straightforward, very, very classic, easy two-pointer solution. But I could have made a mistake. Like I said, I'm worried about line 10, whether that should be truly less than or equal. So let's go through a couple of test cases real quick. Not actually running code, to kind of talk through it and see whether this is the result we expect. So let's do case 1. So I'm going to do the visualization I was doing earlier. So let me write this out real quick. I know I could have copied it, probably next time. And we're going to put start. We're going to put start at -4. And then what we're going to do, I just heard a noise. I missed it because I'm new to Twitch. But thank you for whatever just happened. Thank you for following me, Dungeoneer 3. Appreciate it. So what we're going to do is we're going to set start and end. So start is going to be the 0th index, and then end is going to be the last value. And now we're going to go through our iteration. So start is set to 0. End in this case is going to be 5 because the list is 5 minus 1, which is 4. So 0 and 4. And now we're going to come into our loop. So 0 is less than or equal to 4. That's true. So let's go ahead and run through the loop. So start squared is going to be nums at start literally to the power 2, so it's squared. So in this case, nums at 0 is -4. -4 squared is 16. Okay, There's something else we're going to have to do. I actually just realized this algorithm's not going to work. Let me explain what the problem is. So there is actually, and we actually have to do this backwards. I'm so sorry. I just remembered what I need to do for this one. So but let me explain why this approach is not necessarily correct. So what's going to happen here? If I compare 16, which is nums at 0, and I compare nums at 4, which is 100, 16 is obviously going to be less than 100. So per what we just previously described, we're going to put number 16, right? But there's no way that's correct, right? In fact, it's completely wrong because we already know from the output, and just because we're all reasonable humans, it should be 0. So what we would get in this case is if you did this approach, which is wrong, you would get 16, and then you would get 1. So let me just kind of grok what this would end up being. It would be 0, it would be 9, and then finally you'd get 100. That's not what we were looking for, correct? So the way that this actually needs to be solved, and this is a cute little trick we can do, is we actually want to build this list in descending order. And let me explain why that works real quick. So I apologize for leading us down the wrong route, but like I said, we're practicing in here, we're human, and we're learning together. Yes, Blue, I think it should be less than and not less than or equal. Let's fix the first part of the algorithm that I said I made the mistake on, and then, yeah, we'll take a look at that as we kind of go through the solution. So what we want to do instead is we actually want to flip our logic, and we actually want to take the greater than. So the idea here being is that we always want to take the greater of the two values and push them. And let me show you why that works. So let's kind of go back to our case where we're starting at the ends. So we compare 16 to 100. If I always want to take the greatest value, we take 100, right? So we take 100, and then n goes down to index 3, which is 3, right? And then we compare again. So now we compare 16 to 9. Well, what's the greater of 16 and 9? It's actually 16, right? So we're good. So then what happens is start pointer goes to -1. So now we compare. So now if we do the comparison, it's going to be 1 and 9. What is the bigger of the two values? The answer is 9. So now end pointer is going to shift to 0. So what is the greater of 1 and 0? Well, obviously it's going to be 1. And then finally, we have one value left, which is 0. So 0 squared is 0. So what does this end result look like? Well, it looks like the answer that we were actually trying to get to, but it's just in reverse order. So a way to handle this is just to simply take our final result that we've done and just do a simple logical reverse. So if we reverse the final solution, which is in ascending order, then we basically get the solution we're expecting. Now, that being said, we could do some other solutions where we try to modify things in place or otherwise kind of work around this. But I think for the sake of this explanation, this is the solution I would give. And then if I wanted to give something a little bit more efficient, because the issue with this is that you're going to have to run through your data one more time, right? Because you have to do another n run, or n being the length of the number of things to do, because you're going to have to move everything and put them back into a new place. But I think for today, this should be sufficient. Okay. Long story short, now that we've kind of talked about why our approach was wrong, and we realized that we need to basically invert our thinking, let's go back to our loop, which is where we have the core algorithm implemented, and let's fix it. So case 1, what we want to say is start is greater than or equal to end. So in this case, if start is greater than or equal to end, we push start, and we still increment by 1 because we're still moving the pointers inward toward each other, so that part doesn't change. Else, if start is less than end, then we push end. So it's not a big change to the algorithm, it's just a subtle shift in the logic that we're trying to do in this instance. So now that I believe we fixed the algorithm, let's go ahead and run through this now, case 1, example 1, and see if what we said is true, which we actually did case 1, so we're going to skip that because we already solved it, right? That's what we did before we started this algorithm. Let's go ahead and go to example 2 for time's sake. All right, so I'm going to reset our pointers. So I'm going to put end back here, and then the values I'm going to update to match the example. So 7, -3, 2, 3, and 11. Now, one thing I want to mention on this stream is that I don't prep for these problems. I've done some of these in the past, preparing like for other things, but it's been months since I've last done this. So in a lot of cases, I'm basically reimagining the problem. I don't prepare solutions for these streams. Like you'll see sometimes on YouTube videos where they're going to give you the perfect answer because it's written out on a piece of paper and they just step through it. I'm going to make a lot of mistakes. My hope is over time, and talking to you, the chat, and kind of trying to grok what's going on, we make less mistakes. But this is not going to be one of those streams where I give you a perfect answer. So thank you. All right, so now let's look at our example 2. So -7, -3, 2, 3, 11. Let's go through our algorithm. So the first comparison we're going to do, it's going to be 49, which is 7 squared, and 11, which is 121. Well, the larger of the two values in this case is 121. So I'm going to create a new array, which is going to kind of represent our virtual new array, and I'm going to push the number 121 into it. So since we used 121, end is now going to go to this indice. So now we do the next comparison. So we do 49 and 9. 49 is bigger than 9. So 49 goes into the slot. And then we're going to push start up to, oops, I apologize. We're going to push start to position 1. So the next iteration, we're going to do 9 and 9, right? So because start squared is going to be nums at start squared, and then n squared is nums at n squared. We're squaring it each time, then we're just doing a simple logic comparison of values. So this is our tiebreaker case, but no big deal. Like we discussed, start is going to be greater than or equal to n. So in this case, we're just going to take start. So we're going to push. So what we're going to do, oh my gosh, sorry. We're going to push 9. And since we took start, start is going to move to 2. So now we do the next iteration. It's going to be 4 and 9, which is the bigger one. Well, in this case now it's e, which is what I meant when I said earlier that effectively it's now going to become, how do I say this? It's now it gets taken next, and that's what I meant when I said basically it doesn't matter which you pick when there's a tie, just as long as you pick one. So we pick that one. So we push the value of 9 again to the array, and now start and end are both at 2. So with start and end at 2, well, 4 is greater than or equal to 4, right? Because they're the exact same number. So this is kind of a weird case, but it happens when we have an odd number of entries in our list. So then we're going to push the value of 4. And in this case, now start is greater than. So remember we talked about whether we needed this to be less than or equal to? I think it has to be less than or equal to. And the reason why is to handle this scenario when we have an odd number of entries into the list. Because if we change this algorithm to just be less than, we would have skipped the number 2, because when they were tied, we would have not run that entry and our list would have been missing one value. So I think less than or equal to is correct in this case. Okay, so from these two entries, I have reasonable confidence. And then of course, that list we just showed gets reversed on line 26 using array.reverse, which is a built-in method, array method in JavaScript. Okay, so let's run our base case to see if we're on the right track. And we are. So with our input, our output was 0, 1, 9, 16, 100. And our expected case was our expected value was 0, 1, 9, 16, 100. So, oh, thank you so much, Blue Lily. I'm definitely trying to learn on the go, so I appreciate it. And thanks for joining us in the chat tonight. So I have pretty reasonable confidence that this algorithm should work. Are you guys confident? Or I should say y'all, I apologize. I'm pretty confident. Let's do it. Let's submit it. And we succeeded in our first submission. Everyone give yourself a round of applause for participating and making it through the explanation. So, wow, we solved 2 problems tonight in our first try on the grader. That's awesome. Now, I'm going to fully admit to you, that's not going to happen very often. And the reason why is there are a lot of algorithms like dynamic programming, linked lists, graph theory, that I just don't have very much exposure to because I don't think I've said this in another stream, but I have a background in electrical engineering and not computer science. I'm a self-taught developer, essentially. I mean, I learned assembly and C++ in college, but I taught myself JavaScript to get into front end. So I'm kind of learning, I'm starting to learn more of these CS concepts. And part of the way I'm hoping to do it is through streams like this. So here's where we're at. Okay, we're at 54 minutes. It's actually 11:30 here in Dallas, which is where I'm based. So I think this is a good time to close. I wanted to thank everyone who joined, who's still here. I'll be again streaming, I think, almost every day because I want to keep a consistent cadence. and hopefully we'll be able to have some fun and learn together. So thank you so much for joining, and have a pleasant day or night, depending on where you're from. Take care.